Today, we're going to pull back the curtain on the hidden rules of physics. These are the rules that control everything that moves, from a planet sailing through space to a simple spinning top on your desk. So think about this for a second. A cannonball flying through the air, a kid on a merry-go-round, a pendulum and a grandfather clock. I mean, they couldn't look more different, right? But what if I told you they're all playing by the exact same, surprisingly simple set of rules? All right, let's dive in and actually reveal these hidden rules of motion. First up, let's talk about that cannonball and its two-dimensional journey. We're going to unpack that arc. So what even is a projectile? Well, it's pretty much anything you throw or launch or fire and then just let go. Think of a baseball after it leaves the bat or a diver after they jump off the board. The second that initial push is gone, gravity is the only thing in charge. It's the boss. So how in the world do we predict that graceful curved path? Well, here's the big secret. You don't. You kind of cheat. You take that one complex two-dimensional problem and you break it into two way simpler, totally separate journeys that are just happening at the same time. And here's how that works. Horizontally, once the object is flying, there's nothing pushing or pulling it, so it just coasts along at a perfectly constant speed. But vertically? Oh yeah, gravity is pulling down on it, constantly, changing its speed every single second. The real key here is that these two journeys are completely independent of each other. And this brings us to the two golden rules for any projectile ever. Horizontally, the acceleration is 0, period. Vertically, the acceleration is always the same. It's a constant we call g, the acceleration due to gravity. And believe it or not, that's the entire secret. Okay, so we've covered things moving in an arc. Now, let's shift gears from straightish lines to curves. What does it actually take to make something spin and rotate? Time to get into the physics of spinning. You probably remember Newton's first law, right? An object in motion wants to stay in motion, in a straight line. It's just its natural tendency. So if you ever see something turning or moving in a curve, you know for a fact that some outside force has to be making it do that. Things just don't turn on their own. That turning force has a pretty cool name: centripetal force. Now, this isn't some new magical type of force. Think of it more like a job description. The force could be tension in a string, or gravity holding a planet in orbit, or even the friction from your car's tires on the road. Whatever it is, its one and only job is to constantly pull the object inward, toward the center of the circle. And this quote just nails the concept. Imagine swinging a ball on a string and then the string snaps. The instant that inward pull, that centripetal force, disappears, the ball just flies off in a perfectly straight line. It's finally free to do what it wanted to do all along. Okay, so we get it. Centripetal force keeps something moving in a circle. But what gets it spinning to begin with? You can't just push on it. For that, you need the rotational version of a push or a pull. You need a twist. In physics, we call that twist torque. And torque isn't just about how hard you push, it's all about where you push. I mean, think about opening a heavy door. You always push on the handle, as far away from the hinges as possible, right? That gives you the most leverage, the most effective twist, the most torque. And what's really amazing is how the physics of spinning is basically a mirror image of the physics for moving in a straight line. For every concept like distance, speed, and acceleration, there's a rotational twin. It's almost like learning a new dialect of a language you already speak fluently. All right, for our final piece of the motion puzzle, let's go back to that grandfather clock. We're leaving behind arcs and circles and diving into the steady, repeating rhythm of things that oscillate. This kind of rhythmic dance is called simple harmonic motion, and it describes basically anything that swings or bounces back and forth around some central point of balance. We call that balance point equilibrium. It's the place the object would just hang out if it wasn't moving. The absolute hero of this entire story is the restoring force. Its only job, its only goal in life, is to drag the object back to that middle equilibrium point. The farther you pull a pendulum to the side, or the more you stretch a spring, the harder that restoring force pulls back, shouting, "Get back to the middle!" Now, the two classic examples you always see are the pendulum and the mass on a spring. And what's so fascinating is that the things that control their rhythm, what we call their period, are completely different. For a pendulum, its rhythm depends only on its length and the strength of gravity. But for a spring, it's all about the mass that's bouncing and how stiff the spring itself is. Okay, now get ready for a bit of a brain bender because this part is really counterintuitive. At the very bottom of its swing, the pendulum is moving at its absolute fastest, but at that exact instant, its acceleration is zero. Then, at the very highest points of this swing, where it stops for a split second, its velocity is zero, but that's where the restoring force is strongest, which means its acceleration is at a maximum. It's totally backward from what you'd expect, but that's the heart of how this motion works. So we've dissected the arc, the spin, and the swing. Let's step back for a moment and see how these hidden rules all fit together to paint one big, unified picture of motion. So it really all boils down to this. 4 simple ideas for 4 types of motion. For projectiles, you just split the problem in 2. For circular motion, you need that constant inward pull. To get something to spin, you need a twist, a torque. And for that rhythmic back and forth motion, you need a restoring force that's always trying to get back to the center. And that kind of leaves us with a final pretty big thought. If these few simple rules can describe everything from the orbit of a planet down to a vibrating guitar string, it just makes you wonder, right? What other incredibly complex patterns in our universe are secretly being governed by beautifully simple laws, just hiding beneath the surface, waiting to be found?